Swayam Prabha. Digital India. Educated India.
Thank you for being here on a Saturday and tomorrow on a Sunday. I apologize for forcing you to do that due to my schedule. So I think it would be best if I talk about a bit more about additive manufacturing of ceramics from precursors. And today I will talk about additive manufacturing of ceramic matrix composites. So yesterday there was a question concerning how to make I was saying that there was a question concerning toughness of ceramics, and someone mentioned that it would mention the possibility of adding fibers to increase the toughness of ceramic materials. And of course, this has been done using both short fibers and continuous fibers. So people have developed what are called ceramic matrix composites, and there is a major difference between conventional plastic-based composites, fiber-reinforced composites, and ceramic matrix composites. And the difference is the interface between the fibers and the matrix. For a conventional polymeric-based composite, what you need is the reason why you are adding the fibers is typically to increase the elastic modulus of the part. And in order to achieve transfer load between the external stress and the matrix, you need a strong bond between the matrix and the fiber. So you add the sizing to the fibers that connects chemically both to the fiber, typically carbon or glass, and the matrix. In this way, you can have the load transfer, and the fibers can actually increase the elastic modulus of the part and the strength of the part. For ceramics, the reason why people add fibers is not to increase the strength, because actually fibers often introduce defects and reduce the strength of the part, but it is to increase toughness. And you know that the problem with ceramic materials is catastrophic failure, and due to, of course, the fact that the dislocations cannot move due to the covalent or mixed ionic covalent bonds in the material. And therefore, the strategy is to try to increase the pathway that the crack has to go through before fracturing the component. So the fibers serve the purpose of deflecting and the cracks, increasing the work of fracture required to separate the part into two the component into two parts. So in order to achieve that, you need a weak bond between the fibers and the matrix. So the strategies for doing that, for using fibers in a ceramic material are completely different from the strategy and the reason for adding fibers to a different material. So people have been making carbon-carbon composites reinforced with different types of fibers, and ceramic matrix composites using different types of fibers. And often the matrix for the ceramic matrix composites is based on silicon carbide, or depending on the process you use for making them, based on silicon oxycarbide, with different, of course, temperature limitations. So people have been making ceramic matrix composite for quite a while. They are dual-use materials for a lot of military applications, defense applications, and of course other high technology applications. For instance, inside a nuclear fusion reactor, you can use graphite and silicon carbide, and a lot of components in the ITER fusion reactor in France. The European fusion reactor contains a lot of silicon carbide ceramic matrix composites. The way you make the ceramic matrix composites is a little bit complicated. There are different possibilities. I'm not going to discuss how to make a composite, but what I want to say is that there is not a lot of work on additive manufacturing of ceramic matrix composites, because it is not easy to apply additive manufacturing technologies to the fabrication of CMCs. So today I will be discussing some of our activities in this field. And first of all, let me mention that you know that we have a wide range of additive manufacturing technologies that can be used for developing parts using ceramic feedstocks, powder-based or precursor-based. And if you think of the requirement of adding fibers, then you understand that a lot of these technologies cannot be used. Distinguishing between chopped fibers and continuous fibers. Chopped fibers, you could think of adding them, for instance, to a powder bed system. So while you're spreading the powders, you can also spread the fibers. But what happens is, for instance, if you're using carbon-based fibers, they have a lower density, and with respect to the ceramic powder, and when you try to spread the layer of mixed powder and fibers, the fibers tend to go to the surface, and then when you recoat the part, they tend to be pushed out from the powder bed. So that's not a really viable approach. If you're working with DLP, then having carbon black fibers inside the feedstock doesn't help and prevents the system from being cured. So the best approaches are based on extrusion. And there are people that make, at least for polymers, that make filaments that contain both the matrix and continuous fibers. Nobody has done that yet for ceramic materials. I think that's a viable approach. There are some examples in the literature where, for instance, they have a system that pushes the fibers into a nozzle, and on the other side you have a molten pre-ceramic polymer that is pushed inside the chamber, and in this way you can print continuous fibers. You have issues in terms of placement of the fibers within the filament that has been printed. And in any case, when you have continuous fibers, you should also think of ways of cutting the fibers when required in an automated way. So it's quite difficult to do that. Coming back to this slide, so besides having a filament made that contains both continuous fibers and matrix, one approach that people can have been using is direct ink writing. And you can see here, this is one of our earlier setups. So we have, in this case, a syringe with a piston, gas-operated piston. We typically do not use an extruder with this application because we do not want to damage the fibers when they go through the extruder's screw. So this is quite easy setup to manage. You simply have to make your feedstock in such a way that it contains the appropriate amount of fibers. And there is something interesting that happens in the nozzle when you have short fibers. And this is the fact that the fibers get unlined by the shear stresses along the direction of the filament that has been extruded. So this provides additional benefits to the behavior or mechanical behavior of the material. We were actually the first ones to demonstrate that you can 3D print a ceramic polymer with chopped fibers and make a ceramic matrix 3D printed composite in this way. Of course, in a composite, you would like to have a large volume of fibers, but if you try to mix your ink or your ceramic polymer with the fibers, then you realize that above a certain volume threshold, the fibers start to become interconnected within the volume of the ink, preventing extrusion. So we started with a little amount of fibers, and then we proceeded to increase it to 20 volume%. And we controlled the rheology of the ink using a little bit of colloidal silica, and we used a large nozzle tip in order to be able to extrude efficiently the material. And the dimension of the fibers have a diameter of between 6 to 8 microns, and these are chopped fibers with a length of 150 microns. On the market, you can find carbon fibers from, let's say, 60 microns to 200, 300 microns. And we just printed a structure, and in this case, a scaffold structure. You can see the fibers aligned in the, especially here, you can see the fibers aligned into the strand. After pyrolysis, what happens is that the matrix shrinks, of course, because you have the polymer to ceramic conversion, but the fibers do not shrink. And since there is some adhesion between the limited, but it is present, adhesion between the matrix and the fibers, what happens is that you have hindered shrinkage. So the matrix wants to shrink, and the fibers oppose that shrinkage. And this leads to cracking of the filament, and cracking which is perpendicular to the fibers. So here you can see cracked filaments after pyrolysis, but you can also see the very nice distribution of the fibers within the filament and the alignment of the fibers along the axis of the filament. So this is initial work, and I forgot to mention that one of the mechanisms in ceramic matrix composites for absorbing energy and therefore increasing the toughness of the composite is the so-called pull-out effect. So basically you extract the fibers, short fibers get extracted from the matrix, and this requires additional work rather than simply for the fracture to go through the diameter of the filament. So pull out is something that you want, and if you achieve that, it demonstrates that you have a weak interface between the matrix and the fibers, which is what you want. So on one side, these initial results were promising. On the other side, you can see the issues that we have. So in order to reduce the shrinkage, what you can do is, of course, add fillers, because you're substituting volume or part of the volume of the material that shrinks with part of the a material that does not shrink. So we added silicon carbide particles. Of course, you can choose a wide range of particle sizes. We tested different ones, but 1.5 microns worked well. And note that, of course, you can add different amounts. Note that if you add particles to your system, then the viscosity increases, and this leads to difficulties with extrusion. So if you add particles, other solids to the ink, you need to reduce the amount of fibers. So we went down to maximum 17 volume% of fibers in these experiments. We tried also to print with smaller nozzle tips, and we were able to do that. And you can see that after pyrolysis, basically there are no cracks in the material. I mean, if you go and look, you can find some minor cracks, but that's not but the system is much better than before. You can see here the silicon carbide particles well distributed within the ink, and you can see some fibers as well. So we wanted to look at the pull-out, and therefore we looked at the cross-section, and you can see that we have, in this case, a little bit more limited pull-out, but we have some pull-out. So you can see the fibers, and in some cases you have holes because the fibers have been extracted, and in other cases you have fibers protruding because on the opposite face you have holes corresponding to the position of the fiber. You can see that the fibers are well distributed within the filament. We had some voids due to the incorporation of air inside the ink. Now we are doing a defoaming step that allows us to remove most of the trapped air. So if you look at the cross-section, you might say that you have pull-out, but in order to be sure, we needed to also carry out additional experiments, because you can have a pull-out effect simply if the matrix crumbles around the fibers during fracture. So this is not by itself an evidence of composite behavior. So we carried out 4 point bending tests. We prepared a rig that allows us to pull our filament and break it in 4 point bending. And you can see that we were able to achieve a composite behavior. Certainly you're familiar with the fact that if you have a linear elastic behavior, the fracture happens a very limited deflection values, and you do not have an extensive region where you are breaking your sample, continuing to break your sample, absorbing energy, and having a toughening of the material due to the fiber pull-out and due to the fact that the crack has to go through the fibers, around the fibers, leading to the final fracture of the component. So this is evidence of the composite behavior of the filaments, and therefore confirming that we do have pull-out inside the system. We then tried to develop a system, in-house system, that allows us to print continuous fibers. We had a contract with a defense company in the US, in England, Kinetic. And we tried to come up with a possibility for co-extruding fibers, continuous fibers, and matrix. So my student came up with this approach where you have a continuous fiber spool. And one of the things that I should mention is that the fibers are, of course, the continuous fibers are, of course, dry. You can have strands with 3,000, 6,000, 12,000, 24,000, 36,000 strands, fibers within the same toe. And there's nothing between the fibers. There is a void. So having such a fiber toe surrounded by the matrix is not good enough, because the fibers in this way are not able to sustain the load, as if in the case when they are surrounded completely by the matrix. So what you need to do is that you need to infiltrate the fiber toes with the matrix, so that you have the entire system that doesn't contain voids. So we not only have the fibers that can be extruded, but we also have a prepreg chamber. And of course, here we can put our silicone resin material that allows us to prepreg the fibers before they are met by the matrix and extruded. So you simply have, there is no motor up there, so the fibers are extruded, they are not pushed. So you simply pass the fibers the first time, and then you increase the pressure, and everything is pushed out. So this is a system that worked, but not really nicely for reasons that I will explain in a moment. So we modified the system, and using an approach where we have the fibers coming from the side, and we have the matrix that is being pushed, and we have two channels that allow us to have a better distribution of the matrix around the fibers. So here you can see the results from the first approach, and you can see that we have extruded filaments that have the continuous fibers well placed within the center of the filament. This system contained also, the matrix contained also silicon carbide particles, but they were not in an amount sufficient to prevent cracking after pyrolysis. Bear in mind that when you make ceramic matrix composites, one of the approaches is to use pre-ceramic polymers as a matrix. And so you have a fiber sheet, and you pre-preg the sheet with the pre-ceramic polymer, and typically also some particles. And then you simply lay your fiber sheets one on top of the other. You press, you cross-link, you then pyrolyze. And you will certainly end up with a cracked matrix. So what people do is that they subject the part to a PIP cycle, pyrolysis, pyrolysis, infiltration, and polymer infiltration and pyrolysis. So they infiltrate again the matrix with the same pre-ceramic polymer. They pyrolyze it again. In this way, they start healing the cracks. And typically, if you want to have a crack-free component, you have to do this up to 10 times, which is what people do because they don't have any other choice, but it's not really ideal. So having 3D printed cracked part is bad, but it is still acceptable because this is what would happen anyway. Here you can see, well, the images are not really nice, but you can see again the filament with the matrix with the particles, and you can see here the fiber toe that is placed in the center of the filament. And we tried also to re-infiltrate. In this case, you can see a crack here. Down here is the fiber toe. This is a cross-section of a filament. This is the matrix. And you can see that we infiltrate the crack with the pre-ceramic polymer solution. And here you can see some cracks that have been healed because of the infiltration with the additional preceramic polymer. Of course, we also have issues. So the light part is the mounting epoxy that infiltrated some porosity and was not possible to eliminate, and that's why you have this bright spots. But you can see some of the defects that you can have when you do this kind of printing. You can have the fiber toe that is not really placed well within the matrix, or you can have some residual porosity. But if you look at the infiltration of the fibers between the infiltration of the matrix between the fibers, you can see that with this pre-pregging approach, it is rather the result is rather good. It's not perfect. We have some regions where we still have some voids, but you can see that the matrix there is enough matrix between the fibers. So this is again the same type of approach with the fibers coming from a side. You can see here that we can extrude continuously, and you can see here a cross section with the showing after pyrolysis, showing the fiber toes placed in the center of the filaments. And if you carry out 4-point bending, since the part has already some cracks, the strength is not very high, but you can see that we have a composite behavior. Well, this doesn't add much to the information. Oh yes, we carried out also tensile tests because the bending test was carried out to verify that we had composite behavior, so graceful failure as it is called. But people correctly say that if you look, I mean, these are data on mechanical strength, but they are computed based on the supposition that the fibers are placed in the center of the filament. And as you can see here, that's not always the case. So people that work with composites, they don't like this sort of test because it doesn't provide reliable mechanical data. So we submitted a paper, but we were asked to carry out also tensile tests. So because with a tensile test, then you can get real values for the cracking, for the fracture strength of the composite. Before talking about the tensile tests, let me show you here. The stage means simply the number of infiltration post-printing infiltration processes. So this is the original material that contained quite a large porosity due to voids between the fibers and due to the cracks. And then we carried out infiltration steps followed by pyrolysis, and we tested the porosity, the bulk density, and we monitored if we had a change in the size of the filament. And you can see that with infiltration, you can reduce by about half the porosity within the material. And if we look at the different mechanical behavior after no infiltration, after 2 infiltrations, and after 4 infiltrations, you can see that besides reducing the porosity, something else happens. So the sample that had the best the least amount of porosity started behaving in a brittle fashion, meaning that probably what happened is that the infiltration led to basically gluing of the fibers to the matrix. So the infiltration went through the fibers, on the fibers through the cracks, leading to a behavior that is no longer composite. So this means that this approach has some limitations. And these are the tensile tests on the samples, but bear in mind that the samples contain cracks. So again, these are mechanical data that are influenced by that. So the first approach gives you an efficient fiber term impregnation. The nozzle tip can be reused, but we had issues with the incorporation of gas, because when we extrude, we apply quite a high pressure, gas pressure, to be able to extrude everything. And this led to the presence of some gas into the extruded filament. The coaxial setup that we then developed provides advantages in terms of infinite fiber length. And because we are not placing a fiber term inside the printing device, but the fibers come from the outside, we have a good ink degassing, but we have a more limited fiber term impregnation and no reusable nozzle. We are still working on that, and I will show you some data soon. So my colleague, Georgia, she wanted to print a composite structure using, in this case, chopped fibers, and using a robotic arm, like I showed you before. And in order to achieve structures like sandwich panels that you wouldn't be able to obtain by conventional printing. And she was able to add up to 20 volume% of carbon fibers and still obtain a cured system. And the reason why we are able to cure an ink that contains black particles up to 20 volume% is because the LEDs that we placed on top of the at the end of the extruder's nozzle are high intensity. So we have a high UV intensity that allows us to cross-link. You can see that the cross-linking is quite effective. This is the photorheology of the system. We also measured the curing depth, and you can see that we can cure in effectively up to 400 and 450 diameter filaments. And you can see that with the rheology is such that when you apply the UV, then you have a strong increase in the viscosity, which is what you want to enable the retention of the shape. They also measured the fiber alignment upon extrusion using tomography. So if you take these scaffolds and you fracture them, you can see that you have a composite behavior. And they also had the issues that I mentioned concerning the presence of perpendicular cracks. And if you carry out some polymer infiltration and pyrolysis cycles, then you reduce the porosity, you increase the density. So I cannot disclose what we are doing at the moment because we are working with a defense company, but we found a way of, so we modified further the extrusion device, and we are now able to print with continuous fibers. You can see here the fiber tow coming out from the cut filament. But the main point is that we are now able to obtain a crack-free part after one single pyrolysis, because we modified the composition of the matrix in such a way that we can control that more effectively. So this we are hopefully submitting a paper on this soon. So this was the part of this lecture dealing with additive manufacturing or ceramic matrix composites. I hope I didn't kill your Zoom link, because I wanted to, now I would like to switch to a different topic, which is additive manufacturing using sol gel. So how do I exit here? Most of these lectures deal with additive manufacturing, specifically from precursors. And there are three types of precursors that I would like to discuss. So this is the rationale for using precursors and for using often all liquid feedstocks. And there are three different systems that we can consider as precursors for ceramic materials. I already discussed additive manufacturing using pre-ceramic polymers. I would like to discuss now additive manufacturing using sol gel solutions. And I will then discuss additive manufacturing using geopolymer slurries. And these are, again, all the additive manufacturing technologies defined by the ISO standard. Before continuing, I would like to ask, or if you know what sol gel, what the sol gel process is. The sol gel process was developed in the 1980s. There was actually a very good researcher located in Kolkata working on sol gel, one of the pioneers of sol gel processing. And the concept there is that you have a liquid material, an alkoxide, which is simply a metal linked to some alcohol species. So you have, for instance, silicon tetraethoxide. So you have a silicon atom. Where and then you have, let me see if I can. So you have one silicon atom that is linked to some ethoxy groups. So you can imagine a silicon atom. Okay, it has 4 bonds, and attached to the 4 bonds you have ethoxy groups, which is simply ethanol portion ending with the OH group. So you have ethoxy group, which is basically simply ethanol portion attached to the silicon. Okay, so this material can be hydrolyzed if you put it in contact with a certain amount of water and a catalyst, acid or alkaline. And what happens is that you have hydrolysis, so you form silicon with OH groups. And with a catalyst, these OH groups can then condense, forming a continuous network. And you can have a wide range of metal alkoxides, and a lot of them are commercially available, but you can also synthesize them. For instance, you take metallic sodium and you add ethanol, then you generate sodium ethoxide. And what happens is that during with the condensation reactions, what happens is that you form a continuous network and a solid material, which is actually a gel. So it behaves like a gel. It's solid, but it is a soft material. contains residual ethanol and water that needs to be eliminated. So the gel needs to be dried. And then after drying, you can heat it up and form the corresponding oxide. So this approach works very well, for instance, for making small dimensional parts. You can make, for instance, fibers very efficiently with this approach. You can make coatings. A lot of commercially available coatings on glass are based on sol gel approaches because they are very convenient. And of course, you have also a lot of issues in terms of the fact that typically the conversion from gel to ceramic happens with a large volume shrinkage. So this is the alkoxide. Okay, you have 4 of them plus water, and then you start making the OH groups, and these react to form Si bonds. So this is what happens. So people had not yet used additive manufacturing technologies with sol gel systems because there are a lot of problems. One of the problems is the fact that this is condensation reaction is an ongoing reaction. So you have your feedstock, which is this sol gel solution, and it is alive in the sense that the viscosity keeps changing with time, of course, increasing. So if you're using, for instance, DLP approach, you have to make sure that you have a stable system, at least for the amount of time required for processing your part. So I will show you some examples for different projects that we had, and you can process sol gel systems with additive manufacturing technology based on digital light processing. And we also tested direct UV assisted direct in writing. And we've been working with the company Swarovski for generating high refractive index glass. And we have a project where we need to develop parts that have a specific application in the nuclear physics field. So we are developing carbide components. So the sol gel based approach has a lot of interesting advantages. You have a large chemical versatility. You can make oxide, a wide range of oxide materials. You can make non-oxide ceramics by simply adding carbon sources and firing in non-oxidative atmosphere. You have a molecular homogeneity of the different constituents of your feedstock in a liquid. So you have a high homogeneity in the final product in terms of the composition. You can you can design your material by assembling molecular building blocks. You can fine tune in this way the molecular properties, and typically you can use mild synthesis conditions. For instance, you can introduce photocurable functionalities to materials like the one that I've shown here. There are also a lot of issues with this approach. First of all, you need to have a precursor that has suitable reactivity to enable the building of an organic inorganic network with the desired characteristics. So shaping the liquid is not enough. The part needs to be handled. So you need a certain strength, a certain flexibility of the part. You need to control and tailor the synthesis parameters for the sol gel system. So the temperature at which you operate, the pH, the catalyst system, the precursor to solvent ratio.
And you certainly have, as I mentioned, issues with printing. You have solvent evaporation, and the solvent is for conventional salt gel processing, it's alcohol. You have issues with gel strength. You have these ongoing hydrolysis and condensation reactions, which change the viscosity of the system. And even if you're able to print, then you have issues with drying because you have capillary, the gel is micro and mesoporous. You have capillary tensions, and if you evaporate the liquid which is trapped inside the porosity, the capillary forces drag the walls of the pores together, and this leads to cracking. So you need to control drying in a very effective way. And then, of course, then you have to eliminate the organics. If you do photopolymerization, you have certainly organics in there, and you need to sinter. In our approach, we decided to use high boiling point solvents, because instead of conventional solvents like alcohols for the salt gel system, because in this way we have a low loss during low evaporation during printing, and we generate some transient porosity for debinding. And we decided to generate two co-continuous and linked networks after photopolymerization. One organic network based on photopolymerized acrylates, and one inorganic network based on condensed MOH groups from the hydrolyzed metal alkoxides. In this way, we were able to achieve both flexibility and strength of the network. So the company is Swarovski, which is famous, of course, for crystal glass. And crystal glass is a material that has a high refractive index. So we need it, and silica is the glass that has the lowest refractive index. So we decided to modify the composition of silica by adding titania, which is typically used also in fiber optics to increase the refractive index of pure silica. But there are some limitations in terms of the amount of material that you can add while retaining transparency. So with titania, you are not able, we typically able to go above a certain value for the refractive index. But zirconia works well. It allows you to have a high refractive index. So we used those alkoxides, commercially available. We added organic acrylate photopolymer, and we also added a silicon alkoxide acrylate, which is capable on one side to link to the gel network, on the other side to link to the photopolymerized organic network. And then we sintered at a low temperature. If you use a colloidal silica-based approach and additive manufacturing, you can get transparent glass at 1400 degrees. With salt gel approach, you can get a transparent glass at lower temperature. And bear in mind that if you want to use colloidal silica to obtain glass, because since you have to fire at high temperature, the problem is that you cannot dope silica with other constituents, with other oxides, because you tend to crystallize, and therefore you lose transparency. So with this approach, we were able to generate high refractive index. I will show you some values, and transparent glass that we were also able to color by simply adding chromophores to the feedstock. And we developed photocurable formulations that are suitable for UV-assisted direct inviting and for digital light processing. So here you can see the silicon precursors that are in the system. We also added this modified alkoxide, because the silicon methyl bond provides flexibility to the gel network, so we can reduce the stresses within the network. And this is the silicon alkoxide that has photopolymerizable moieties. And in order to modify the refractive index, we added zirconium and titanium alkoxide. And first, let me talk about direct writing, UV-assisted direct writing. You can see that we can print the part, it retains the shape, and this is, of course, before sintering. And after sintering, we were able to obtain transparent, high refractive index parts. This is a fast approach for 3D printing, and it works well for fabricating tall geometries with large spans and thin wall features without sagging. Of course, you can see that you have the stair-stepping effect on the surface of the component due to the extrusion through a nozzle. The ink requirements are that you need a shear thinning behavior. We already mentioned that. And tunable viscosity, because we used the solvent evaporation as a way of controlling the retaining of the shape. And by applying UV to the feedstock, you can see that you can trigger the photopolymerization very quickly, and because the solution is very transparent, and increase the viscosity. So we were able to print parts, and at the beginning we had issues because we were working without adding a highly boiling point solvent. So after sintering, the material was transparent, but we had a lot of cracks. After adding the high boiling point organic solvent, and after sintering, you can see that we can obtain a fully transparent glass. And we monitored the presence of nanopores or mesopores inside the material due to the introduction of the highly boiling point solvent. And you can see that indeed we were able to introduce these pores inside the part, which helped with the organic burnout. So you can see here another part that was printed, in this case using digital light processing. This is a Voronoi structure, and we have unlimited design freedom. We can print complex parts, and the sol gel solution has a very low viscosity, so this works well for the DLP approach. Specifically for the DLP approach, we need, since it is a layer by layer approach. So I already mentioned you're printing your part, okay, and you need the part, and this is the liquid surface. You have just photopolymerized, the light comes from the bottom. You have just photopolymerized your layer. You need to lift your part. The liquid fills the gap, and then you photopolymerize again, and you lift by one layer's thickness, okay? So the issue is that there is adhesion forces between the printed part and the surrounding liquid. So if the strength of the printed part is not good enough, the part will break, or if the attachment to the top of the moving stage is not strong enough, the part will detach. But this you can solve. But the strength of the network that you have formed needs to be sufficient for allowing the pull-up. And there are, depending on the printer, you have different forces that are applied. So it's difficult to give an absolute value for the strength that you need in order for the process to work. And a gel does not have a strong enough, doesn't have enough strength to withstand this lifting, and therefore we made sure that we were able to develop an organic photopolymerized network inside the system in order to provide enough strength to withstand the stresses from the forces exerted during the printing operation. So we have a partial decoupling of the photopolymerization derived organic network from the inorganic one using acrylic acid. So you can see here the continuous sol gel inorganic network and the organic photopolymerized network coming from the presence of acrylic acid. And by the way, acrylic acid also serves the purpose of chelating the zirconium precursor, because the zirconium precursor tends to hydrolyze faster than the silicon precursor, and this would lead to agglomeration of zirconia rather than having a homogeneously distributed system where you have zirconium and silicon well distributed. So in the end, we were able to print, as you can see, and transfer and successfully obtain transparent high refractive index glass. And you can see here the reference fused silica glass with a very low refractive index. And this is the type of values that we were able to obtain. The Abbe number is also important for these applications. And of course, you need high refractive index because you know that the reflectance from the surface of a glass is related to the value of the refractive index. So the higher the refractive index, the higher the amount of reflected light, so the glass is more sparkling. And if you work with jewelry, you want sparkles. So that is why we developed this. You can see here the transparency of the S-printed glass. And of course, transparency is never 100% because you have reflection at both surfaces. So typically 8% or a certain percentage of light is not transmitted. And then if you add coloring agents, you can have different colors. And of course, the color in glass is complementary to the absorbed wavelength. So if you absorb in this region, the color comes from this side or from this side. If you absorb in this region, the color comes from the radiation that is not absorbed. Because if you absorb, you're not transmitting, of course. Okay, so we were able to achieve refractive index values up to 1.72. Transmittance can be as high as 98, almost 99%. For crystal glass, the density is also very important. And we are within the range of crystal glass, which is what we wanted.
Just curious, like you have printed uranium carbide. Like,
yes,
did they allow you to print in your facility?
So the student had to go to a special facility in Germany where they can handle hot materials. Yeah.
And like since as you said, some of the materials are as sensitive, like the zirconium precursors are moisture sensitive. Did you use some controlled atmosphere for the printing? Like it's follow back for the on the other day question.
Okay, so in the sol gel system, you need to add enough water to generate a fully hydrolyzed precursor. Otherwise, you will still have an unreacted, okay? And we added, if I remember correctly, half of the stoichiometric water in the system because other water was coming from the environment.
So you're more or less using a single source precursor. So it's kind of as stable. Is that what the takeaway?
So this
For
is a
black printing?
this is a sol gel system. So it is an unstable system because you have ongoing hydrolysis and condensation reactions. So it is homogeneous, but it has a certain pot life. So you need to use it within the time frame where the viscosity is not changing too much.
And also the volume, like Solgel typically, sorry, DLP typically wants a bigger volume, like
Yes.
requires a bigger volume. So do you have a printer that can print in a small volume? Because I can see your print size is very small.
Yes. So we modify all our VATs in order to be able to work with a smaller amount of material, less material. Yeah. So we develop. We use an additional. We put an additional smaller chamber on top of the original one, inside the original one.
Short fibers, then due to the shear stress, the directions are controlled. Is it advantage? Because the purpose of using the short fiber may be the random orientation. But here in your
Well,
case, it is.
bear in mind that you are printing filaments. So if you want random orientation, then you need to, you can orient the filaments. Okay, so you can print a filament in this way, the other filament you can print in this way or this way. Having a unidirectional distribution of the fibers helps with bending.
If the directions are oriented in the same direction, it may be suitable for the tensile loading. What about the other loading conditions?
So that's the beauty of additive manufacturing, because you can design a component that in which the filaments are oriented in a way that allow the entire component to respond to external stresses based on the architecture that you have given. So I'm not a mechanical engineer, but you can design parts where you can put the material where you want it for responding to certain stresses.
In case of additive manufacturing for CMC, why did we particularly choose 4-point bend test instead of 3-point bend test to characterize the strength of these materials?
So ideally, one would follow a standard for testing. And if you look at the standard, it tells you what is the span that you need to use. And so I think we followed the standard.
And how do we improve the adhesion between the matrix and the fiber? Is there any surface treatment that has to be done before?
Yes. So actually, you want to debond. You want to debond the fibers from the matrix. You want to separate the fibers from the matrix, or rather, you want to have a weak interface. So in commercially available CMCs, what they do is that they coat the fibers using CVD, and they typically put a layer of boron nitride. In our case, we did not perform any treatment on the fibers, and so the behavior can be further improved if we go through the step of adding coating the wood better. They would allow for a better interaction between or lower interaction between the matrix and the fibers.
So the work required for a pullout will be even more higher if we have a...
Yes, yes.
And also for there was a slide on stage 1 to 5, which was
Yes.
showing the porosity, density.
Yes.
In that one, while going through multiple cycles, will that thermal cycling not affect the fibers that is there? And will it not affect the interface between the fiber and the matrix, which will also influence the strength value that we obtained?
Good point. So for the fibers, nothing will happen to them because they are carbon fibers that have been produced at much higher temperature. So the fibers are stable. The interface might change because you might further increase the density of the matrix. What we observed is that so we never carried out the experiment where we did not infiltrate, but we fired for 5 times. Okay, so if you do that and then you compare, then you can say, okay, the problem is not the infiltration, the problem is the pyrolysis treatment. But the approach of using multiple infiltration and pyrolysis cycles is standard for people making ceramic matrix composites using ceramic polymer. It's called the LPI process, liquid polymer infiltration process for making ceramic matrix composites. Other approaches include CVD, and you get a very dense matrix, very good behavior, but it is extremely expensive. It takes a long time, like 1 week for making 1 millimeter part. You can use forced CVD, which makes the approach quicker. So the best CMCs are made using CVD. It's very expensive. The least expensive, least performing ones are made using LPI, liquid polymer infiltration, where the polymer is, of course, a pre-ceramic polymer. And intermediate ones with low residual porosity are composites that are made by infiltrating the matrix with molten silicon. This was a approach that was developed by actually an Indian guy, Luthra, in GE, General Electric, in the 80s. A very effective process because you can obtain, so you have your matrix is based on a high yield, in terms of carbon, a high yield polymer. So you have a polymer that you pyrolyze and you generate a porous matrix that is based on carbon. And if you do things correctly, then when you infiltrate with silicon, you react everything apart from the fibers that are protected. You generate a silicon carbide matrix with some residual silicon, which gives you the advantage that the material is fully dense, so you don't have issues with oxygen going through the fibers and damaging them. On the other side, the presence of molten silicon limits the, not molten silicon, silicon reduces the high temperature capabilities of the material. So silicon melts at 1410. So above that, I mean, around that temperature, you cannot go above.
In case of additive manufacturing for sol gel, how did we control the viscosity of the sol? Because I think viscosity of sol will be slightly higher for it to be in a printable format. Or
Yes.
did we add any filling?
So the sol gel precursors are liquid and the viscosity is rather low. When you start the condensation reactions, the viscosity increases, but you can control that by adding solvent. And actually you need a solvent because in order to have the hydrolysis, you need to add water, and TOS and water are not miscible. So in any conventional sol gel process, you add typically ethanol with water, with the correct amount of water dissolved, and this is a mutual, acts as a mutual solvent for water and the TOS.
When we are doing the continuous carbon fiber printing, so once we get a green body, when we are sintering, there will be some amount of shrinkage. So, but the fiber may not be going for a shrinkage.
Yes.
But how does it incorporate?
So you're right, this is a major problem. So one approach to reduce the amount of cracking is to add inert fillers like silicon carbide. And this works okay for chopped fibers. With continuous fibers, if you only use this approach, you get a cracked part. And again, this would be normal for any CMC processing, so you can live with that, but it's not ideal. We developed a feedstock that allows us to avoid cracking after a single pyrolysis, but I cannot disclose how we do it yet, because we still have to decide if the company wants to patent or we can publish and disclose.
So still, if there is metrics, maybe minor cracks, still it improves the property or from a
So of course, any crack would decrease the strength of the part. But when you make a ceramic matrix composite, what you're looking after, what you want is toughness. So it's you can live with a lower strength but high toughness. So silicon carbide, for instance, I can't think of the top of my head what is the bending strength, but certainly of the order of a few hundred megapascal. Okay. Silicon nitride can go up to a gigapascal. Okay. So when you do CMCs based on silicon carbide, the strength is around 200 megapascal, but you have toughness, which is why you're making the composite.
One more thing, how do you measure toughness? What is a appropriate techniques for measuring toughness in CMC?
Fortunately, I don't work in assessment of mechanical properties because I find that extremely challenging and boring at the same time. So for composites, you look at the presence of graceful failure. So the deflection beyond the elastic part. And then you simply, you go to fracture and then you give the toughness as the integral of the entire curve. For monolithic ceramics, people do controlled chevron notch tests where they look at the crack propagation from the tip of the notch. But you need a specific setup that allows you to obtain a notch with a specific shape in the precise location where you want the notch to be. So people have done that. It's not, I'm happy I don't have to do it. Another way of measuring toughness in an indirect way is to do indentation.
Apart from material versatility, what are the other advantages of sol gel precursor in terms of ceramic yield or something like that?
So I would say that the main advantage of the sol gel approach is the possibility of making a wide range of compositions. So the yield is lower than that you would get with pre-ceramic polymers. So from that point of view, that's not advantageous. But there is an extremely wide range of compositions that you can obtain using the sol gel approach.
Actually, whenever we do printing with the pre-ceramic polymer in DLP, like after printing, it become very rich actually, and it is very difficult to uh, remove the material from the build platform. So, is there any SOP for removing that particular printed component from the build platform? Because sometimes, like we are getting some delamination kind of defects into the structure, particularly when we are printing pure pre-ceramic precursor.
Yes. So unfortunately, I don't have a direct experience on that because I don't even know how to print. Okay, so it's my students and postdocs that do that. Certainly, you have with DLP printing, you have issues of adhesion to the platform and strength of the part while printing. I think my students have more issues with adhesion to the platform rather than detaching from the platform. But I can put you in contact with my students and they can maybe give you some tips on how to improve. I know that the first layers that you print, you cure them to death in order to favor the attachment to the platform. And sometimes we have attached MRA paper to the platform in order to provide a non-flat surface for better adhesion. It depends also on the viscosity of the system, and it depends on the specific mechanism for detaching the part. Because one of our printers, for instance, has a rocking movement, and this creates really strong tensile stresses at the interface between the part and the platform.
So one more question, like the UV assisted direct ink writing, it is similar to wet photopolymerization technique. Both UV as well as we can get a complex shape structure. So in what basis this particular technique has more advantages than SLA or DLP technique?
So, that's a good question. So why would we want to use that approach? Because the building platform can be much larger. So you can print much larger components using direct writing with respect to DLP. And also it is a faster printed technology. So that's the main reason. And you have to bear in mind all the limitations that direct writing gives in terms of shape and a stair-stepping effect, which is much more pronounced.
What about the precision actually? Like geometrical features?
So one thing is the resolution, another thing is the precision. So the precision comes from the placement of the nozzle in the correct place, and the current printers are not bad from the point of view. Bear in mind that you're talking about extruded filaments that have a minimum size of 200 to 300 microns. Okay, so they are one order of magnitude higher, larger than the features that you can get with DLP. So within that range, the precision is pretty good. You certainly cannot. I mean, you can make nozzles that are 10 microns wide, but then you have a lot of issues in passing through the liquid. So we tried to make tip using glass capillary that we break, and we have a 10 micron hollow cylinder, but then the liquid doesn't flow through.
What is your opinion on buried combustion method for pyrolysing pre-ceramic polymer component or sol gel component?
Can you say that again?
Buried combustion method. Like we keep material in the powder, then we do pyrolysis actually.
You mean during the pyrolysis, embedding the component into a powder bed.
Yeah, yeah.
So we didn't have to do that. My opinion is that the gel strength might be a problem. I guess it depends on how much organic you have in the system. We never did that. We do that with other materials, but not for, we haven't done it for Sol gel.